So when you decide to take a shower in the morning, you turn on the water. Do you hop directly into the shower? No, because it's cold. You don't want to do that. What do you typically do? Yeah, you put your hand in it, feel the water, make sure it's right the temperature, right? Are you testing every single droplet of water? No. What you're testing is a sample. Okay? And you might put your hand on one side, and then a little bit later, you might put your hand up a little higher, a little lower. Like, you're testing different samples. Okay? So when we're looking at being able to do large studies, we don't want to look at individual pieces. We want to look at sampling. So typically what you'll see in polling, it's like we'll take the polls, we'll ask a whole bunch of people to get that information. And that can give you a decent estimation of where it is. But when you start looking at what's known as a poll of polls, you look at all the polls, that's where you're looking at multiple samples. And that sample is going to be a lot more accurate and more indicative of what's going on. So first couple of things we're going to look at is how do we get those samples? What does it mean? And those type of things. So here's a plane. This is a plane from World War II that came back and landed safely. The engineers and the military was looking at it and goes, okay, we need to put some armor plating on it to protect the planes. Where should we put the armor plating? Yeah. Where the dots, what? Where the dots aren't? Why?
Because if that those planes get hit and come back, I think planes that got hit out the spot and they come back and over there.
Very good. I shouldn't have asked you first. Most people go, hey, I'm going to put them here and here and here because that's where all the bullet holes are. But that's exactly right. You actually want to look at, well, the planes that didn't come back probably were shot here. Okay. Really easy way to look at it, typically known as survivor's bias. You look at it, okay, I survived, so obviously I did something right. Well, maybe not. You just got lucky and you were shot in the wrong spot. So in this situation, this is known as a bias. We only have the ones who came back. So sometimes looking at the unseen stuff is more important than looking at what you actually have in front of you. Okay? So biased samples are one of the biggest problems that we have. So a sample is biased if it overrepresents or underrepresents some segment of the population. Okay? So we look at biases as like what we dislike, those type of things. In statistics, that's not the way we look at biases. We actually want to know those things. In statistics, we look at it when it doesn't represent everybody equally, okay, or to the level that they should be represented. So when you're looking at grabbing samples, you want to make sure they represent the population that you're looking at in its entirety. All right. Couple things we're going to look at while we're deciding. Wait, I skipped ahead for some reason. There we go. I'm like it jumped. So when we're trying to decide on a sample, the first thing we have to come up with is our sampling frame. This is a list that identifies all members of the population. Okay, so this is important. When you're looking at your population, you want to make sure you list down all the information that is important for your study. So, for example, I want to know what everybody's favorite ice cream is. Okay? If you could choose any ice cream out there, which ice cream would you choose to eat? If you go to the store and look at ice cream, you have cheap ice cream and expensive ice cream. A lot of your cheaper ice creams are typically your standard flavors, your chocolates, your vanillas, your strawberries, things like that. So if you were on the poorer end of the economic spectrum, you might only be eating those ice creams. Like you're not going to be able to afford the Rocky Roads and the Americone Dream and stuff like that. You're not going to be able to afford those. So if I ask you what your favorite ice cream is, you're going to get those. Where if you have money, you might be able to afford some of the other ones. So your favorite ice cream might be Chunky Monkey, for example. Okay? It's a funny one to say. So when you're looking at trying to identify all the members of your population, sometimes you need to look outside of just what's on the surface. You need to look at the demographic information, what kind of things you're looking at. It could be age groups, it could be genders, it could be economic factors, it could be a lot of those things that could have an impact on which you're sampling. And if you don't take those into account before you do your study, that could have a biased effect on your study, because you could be underrepresenting groups of people that you would want represented. Okay. All right. So let's look at a study. So read that real quickly. All right. So question number 1. Is that they did a random sample. Okay. So we've got a random sample. Everybody agree that it's a random sample? Huh? Okay. Why? Why is it not a random sample? Well, it was students in the marketing class, but they're doing the survey. They weren't studying the people in the marketing class. They randomly selected students from the college and mailed them a questionnaire. So they randomly selected 150 students and sent them out a questionnaire. So that makes it random. So if they were only asking in their class, then yes, that would definitely be not random. But if they're looking at, they randomly selected some people and sent it out to 150 people in the college, and that would qualify as random. Next question. Is there any biases that are apparent in the survey?
The 50 students that responded, more like that's interested in the insurance, or not interested in the value.
Okay. So they actually took the time to respond, which can create some bias. Okay. What about the marketing class? Or people who are in a statistics class. One of the first things I told you is always respond to your surveys, right? Okay, but again, not necessarily, we don't know who those 50 students that responded were. So this was just like, if this was a school, we did it here, the marketing class, and some statistics classes actually have you guys do actual studies. I used to. It just takes a lot more time and doesn't really get you the answers that you really want out of it. So if an economics class here decided to do a survey, they would have just randomly picked 150 students from the college and sent it out. It wouldn't necessarily have anything necessarily to do with that marketing class. Huh? Yes, they're conducting the survey. They're not taking it. They're conducting it. Okay. What other biases could be put in play or show up in this?
I feel like since they go to the college, that's pretty biased. Also, it's like.
All right, let's take it a step back. You guys got a survey in the mail for insurance. Would you fill it out? Why? Okay, you have your own insurance. Okay. Well, it's describing your interest in an insurance program. So all the question says, are you interested in an insurance program? Check yes or check the box that fits. Would you fill it out? Okay, so if you already had insurance, you probably wouldn't, right? How many surveys that you've gotten in your mail have you filled out and mailed back? Okay. So then when I said, would you do it? The answer should be no, you're not going to do it. You don't do it now. Okay. So isn't that already an extra bias built in, right? Why wouldn't you fill it out? Some of you have insurance, some of you don't care. Okay. How many of you regularly open all the mail you get at your house? Okay. How many of you regularly open all your emails? More than mail, right? So that's a generational thing, right? The older you are, typically, the more you're going to look at your mail and type of those type of things, and you might notice it. Younger, you might not care. It's like, okay, that's just junk mail. Throw it away. So by mailing it out instead of doing it through email, they might have eliminated a lot more of the younger generation or the younger population. We don't know who responded because we don't have that data or anything else. So, but that might be an internal bias. Who's going to be more interested in insurance? Well, right now you can stay on your parents' insurance till you're 26. That's a new thing. It never used to be that way. When I grew up, it was 18. You were off your parents' insurance, unless you were actively in college, and then you could do it only while you were physically in college till 21, I think, and then you were off it no matter what. So that changed. That matters, right? If you're not even thinking about insurance because you're on your parents, it doesn't matter. If they emailed it to you, would you have been more likely to fill it out? Okay. So you regularly click on links that you get in your email and give them out information? The IT department would not be happy with you right now. So that's the thing. It's like we need to figure out ways to be able to engage everyone. All right. So we got back 50 responses. We don't know where those 50 responses necessarily came from, but it's important to be able to, and we're starting to look at these surveys and look at these studies. Remember, we want a random sample. That's one big important piece, but we also need it to be unbiased. We need that data to be accurate representation of my population. Okay, and that means being able to sometimes look at a variety of different ways. Like we talked about at the very beginning of class, back in September, is I said, how many of you would answer the phone for a pollster? And most of you said, no, you don't even answer. If you don't know the number, you're not answering the phone. Most of you probably, even if you knew the number, wouldn't answer the phone. You're like, why are they calling me and not texting me? It's like those type of things. Like you just don't answer the phone. So that has changed that population there. It's like we've moved from landlines to cell phones. It used to be you couldn't randomly call a cell phone. Now you can because we don't pay for minutes anymore. But we still need to figure out ways to be able to engage all of the population. All right. So we've seen some biases in it. Is it 50% a reasonable estimate of the proportion of all students who'd be interested in the insurance program at the college? So in the survey results, 50% of the students said very interested. Do you think that is an accurate representation of the entire college? That 50% of the population of the college would be very interested in this insurance program. Why? Okay, what was the number I said you really like? Once you get over this number, we're good. Right around 30. So 50 is over that. Would 50 out of the 150 students, you sent out 150 survey. If you got them all back and you got 50%. Okay. So if you look at 50% out of 50 students, how many students actually said they were very interested in the insurance plan? 25 out of all the people that did it. Okay. And if you go off the concept that we said before is like, if you really don't care that much, you're not going to send out back the card, then I'm going to assume that you're on the bottom end of that spectrum and it's like you really don't care. So maybe that's not a really good estimation of it. My last class brought up a good point. It's like if you drive through a neighborhood and you see like political signs, because the election's tomorrow, and you have a bunch of signs, you have some signs for Trump, you have some signs for Harris, and it's like that. that's the same kind of thing here. The people who are extremely excited and interested in it are putting up the signs. That doesn't mean everybody else doesn't care. They're just not to that level enough to actually go out and do something. Like they're probably going to go vote and whatever else, but they're not going to put up a sign and drive down the street with their car blaring and everything else. They're not going to do those type of things. That's the people that would send back the survey. It's like, yep, this is the thing I care. Either you really like it or you really hate it. You're going to send back that survey. Where is my book? There's the book. All right. So what do you think we could have done? What strategies do you think they could have done to get a less biased response? So if I set up a table at the front of the school and I ask people that walk by, is that a random sample? Okay. So that's a big piece, right? It's got to be random. So when that's more of a convenience sample, right? We're taking the people that come to us. And depending on what time you're doing it, if you do it during the day, you're going to get a lot of younger people. If you do it at night, you might get an older population. It's like if you take classes at night, you can see there's a very different population between the classes during the morning and the classes at night. So depending on when you ask, you might get different populations and stuff like that. So we can't just ask the people who walk up to us. All right. So what are some other strategies they could have done?
Did you email and say?
Yeah. Could have emailed. That might have helped. I brought up, it's like a lot, again, it's a generational thing. Some people check their email all the time. Some people don't check their email at all. It's like, so maybe a text message might have worked better for some people, or maybe a group chat through Facebook or Instagram or Snapchat, things like that. Those type of things might have worked. So depending on where they have all the data to be able to collect, they actually have those conversations. So what if I asked everybody in the class? That's not random. Because that goes back to that. Ask everybody in your marketing class, right? Okay. What if I chose one classroom in every hallway and asked everybody in the class? Would that be random? Why? But I'm randomly choosing the classroom. Okay. So there's different ways to get random. So we can sometimes, like most people think of it as a simple random selection. It's like you list every single person down there and you pick every fifth person, or you just randomly pull out numbers out of a hat like a lottery type system. That's one way to get a random sample. There are other ways. One of them is known as a cluster sampling, which is actually what I just suggested with the classrooms, where everybody is broken into the classrooms, but we're going to randomly select the classroom. So that's the random side. And then we would survey everybody in that classroom. So because we're randomly selecting the classrooms, that's the piece that makes it randomized. We don't know who's in that classroom. And as long as we don't necessarily know the class, like the type of class or whatever else, that would eliminate that type of bias in there as well. But we'd have to do it at different times and whatnot to make sure we get a good cross section. So like if I chose, like I couldn't choose this classroom every time because this classroom would have a different type of student in it. Let's say I went through the hallways and I chose room E205 and D208, those type of things, like, and then every classroom I moved one at the night, whatnot, or the next day. That's one way to get a random sampling. So the other thing that we have to look at is how you ask your questions. So a lot of surveys don't just have one question on it. A lot of surveys have multiple questions on it. And they're asking, a lot of times they're asking the exact same thing, just different ways. That way eliminates the bias of how the question's asked and how the answers are presented. If somebody's asking you a question and stating that question to you verbally, a lot of times people will hear the first choice and the last choice and nothing in between. So you have a bias of either picking the first one or the last one a lot more often. So they'll randomize the actual answer choices to be able to determine if that's a bias that's showing up in their actual survey questions. Same thing on ballots. When you're looking at the voting ballots, a lot of times, if you're going down a list, the first one will be the one that more people actually will vote for because it's the first one that's there. And if you don't have a particular preference when you walk in, that's where they vote for. Connecticut's actually very horrible in this situation. Most states, the ballots are actually either listed alphabetically or randomized. Connecticut lists based on the party that is in charge of the highest office. So this year, the Democrats will be the top row on our ballots because the president's running and the president is currently a Democrat. In 2020, when it ran, the Republicans actually had the top lane in office because the Republicans were in office as the president at that time. When the governor runs, it'll be if the governor was the highest office, that will tell you whatever the ballot is. So that's how they decide who's on the top line of the ballot. At least it used to be the machines. You could actually press one lever and vote the entire row. You didn't even have to click all the, it's like this was way before you had to actually walk and click little levers. And they had party line voting. You click the first one and we vote for everybody in that party. Now you have to put the bubbles in every box, which is a little better. So we can start to see how the biases really can start impacting and how we can modify those things. Yeah.
I'm just curious because when it comes to bias, I feel like so much it can create a bias.
Oh, absolutely.
And that's just me.
So there's two different things when you're looking at it. There's bias in your responses, which you're never going to get out. And that's actually something you want. You want to be able to limit that as much as possible in terms of like the first, like not internal biases. Like internal biases, you actually want to know. That's the point. You want to know what the person actually thinks. You want to eliminate biases that are created by the survey. And that's where the underrepresentation, those type of things you can have some impact on being able to eliminate. So like there's a lot of times in the last questions, like who do you want to win or who do you think should win the presidency and stuff like that. They might ask that question. And then 2 or 3 questions later, they might ask, who do you prefer for president? It's like, it's in essence the same type of question, but you might get a different response. So it's like, and those are the ones where they ask a question a few different ways. And if they notice a discrepancy in it, then that question here wouldn't be actually used. So, or they'll ask the same question twice and they'll give you a different person as the first one to see if they can actually weed out those. So there's ways to be able to weed out the answers, the responses that aren't valid
So
or
it's not like
useless.
the bias
No,
bias of
of the actual survey, right? It's a statistical bias, not a personal bias. Your personal bias comes in when you're creating it. That's where you need to internalize when you're trying to create it. It's like, okay, you don't want your bias to come across in how you create your questions. You want to get accurate information. So like, if you want like this, you're really interested, you're going to be making money off this insurance program. You send out the survey, you might have big letters like this amazing program or whatever else. And everything. It's like, because people are going to respond more positively to that than something else, because that's what you want the responses to come back.
they have 3 in the categories positive. 2
Yeah.
negative bias.
Could be. It should be like a neutral one in the middle or no middle number. Like you shouldn't have an interest at all. It's like, okay, very interested, someone interest, not very interested, that middle category. So yeah, there's 3 positive and 2 negative. That could be a bias. You're the first one actually to think of that. I didn't even notice that one. So yeah, there's lots of little things like that. All right. Skip that. We don't really need that. So actually, I'll use one of those. The point estimator is the one that was really important. So a point estimator is a single value calculated from sample data. So a point estimator is basically me calculating it from the sample data that I've got and trying to use that to determine what's going to happen in the population. So it's like, okay, I believe I'm going to find the mean of all these things, and then I'm going to say, okay, I believe this is the mean of the population based on my Podium estimator. The three things we typically will look at is mean, variance, and standard deviation. Those are the proportions, the other one, depending on the type of data we're looking at. The actual full population. So just because tomorrow's election and I've spent more time looking at polling data than anything else at the moment. So when we're looking at the polling data, we look at, okay, this is the percent that we're at. They're going to, with all the data that they've got, they're going to say, okay, right now it's 47, 46, for example. They estimate that the actual population, the popular vote tomorrow, will also be 47, 46. That's their estimator for it, because they've done averaging of all the polls and everything else, and that's where it should end up being. We'll see what happens tomorrow. That's the one thing where when we have elections or we have censuses, it's like we have statistics up to that date, and then we have actual data. So a lot of times when we do statistics, we can collect all the data we want and we can come up with an estimation of what we believe is going to happen, but there's no way to really test if that's true. They do it for all elections, but it's the big ones when the president happens. So basically every 4 years, we have all this polling data and everything else that we have. And then we have the election to actually show, did what we find is actually true? And if it's not, like it was in 2016, they go back, okay, what did we mess up? Where was the biases that came into my samples that I need to address? Okay, and how can we address those? And they make adjustments. And then they did it again in 2020 and they made adjustments. It's like every time they do it, they make different adjustments. You're going to see tomorrow when the polls close, they'll call states with no votes counted. Connecticut will be called for Harris tomorrow at 8 o'clock. Or at 8:01 at the absolute latest, with no votes counted at all. Because the data shows that's the way it's going to go. So when you look at those type of things, that's then still using statistics to make that determination. But at the end, the votes still have to be counted to verify that that was the actual fact. Now, that can have an impact on other places that are still voting. Because now you have people out in California that vote till 11 o'clock our time, and they're seeing all these states called, and they might go, well, I don't need to go out and vote because my candidate's going to win. And that can have an impact on the popular vote. That can have an impact on the state vote and a lot of other things. So there is some things to be said that they shouldn't call anything until the entire country is done voting. But that's the media that we like, instant results. All right. The unbiased parameters, if the average value estimate equals the population parameter, is considered to be unbiased. The three unbiased estimators are the sample mean is an unbiased estimator of mean. So if we find a sample mean, we can use that to determine the population mean. The proportion and variance, and by extension, standard deviation, because standard deviation is just the square root of the variance. Okay, so these are the three unbiased estimators. The top two targets are unbiased. The bottom two targets are biased.
Why?
That was going to be my question. So the top two are equally spread around the center. Yes, target one, all over the place. Okay? Yes, he's a horrible shot. But it's equally distributed all over. So the gun is not the problem. The sights are sighted incorrectly. He's just a horrible shot. Target two, all close to the center, but again, equally spaced around the center. The bottom two are close groupings. Okay. But not at the center. They're off. So, good shots, good close grouping of shots. However, their sights are off. So the gun has the bias that built into it. So they have to adjust their sights because they should have been aiming for the middle. All right. And that's the thing. You want, when you're looking for your data, you want the middle. You want the accurate center. Okay. That's why they're called measures of central tendency. You want the center. So if your information's spread around the center, it's good because it's still giving you can figure out where the center is based on those. Where the bottom two, since they're off on the edge, they're not going to the center. That's why they're biased. Okay, those would be they'd be pulling it in one direction or the other. Okay, does that make sense?
Yes.
Okay, so unbiased, again, you're looking for that center. Not necessarily a nice tight grouping, you're looking for the center. All right. Last major talk piece, and then we're going to actually do some problems. The central limit theorem. Big complicated thing. Very actually simple in practice. Hey, look, there's that number 30. You want a sufficiently large random sample. Random is first, or random is in there. Large just means greater than 30. I know most of us would not consider 30 people large, but greater than 30 is actually considered large in terms of statistics. And it has to be random. Like I could pick the 30 people in this room, that wouldn't be random, it wouldn't fit. Okay. As long as that's true, the rest of the things will be true. They will approach a normal distribution. Okay. You will always have a normal distribution in this situation. The mean, the sample mean equals the mean. So when I find the mean of my samples, I will find the mean of my population. The one thing that changes is how we do standard deviation. So standard deviation for my sample means is the standard deviation divided by the square root of the number of values. Okay. That's important. Because, yes. Yes, it is the population standard deviation divided by my sample size, basically. And that's going to give me my sample standard deviation, or my standard deviation of my sample means. As n gets bigger, what should happen to that standard deviation? Smaller, because as the fraction, as the bottom of my fraction gets bigger, it gets smaller, correct? The fraction as a whole gets smaller. So the bigger my sample, the smaller my standard deviation. What does standard deviation tell me about my normal curve? Okay, so bigger standard deviation means what about the curve? Bigger, smaller. Standard deviation is supposed to tell me variance, right? How varied the information is. The bigger the standard deviation, the more varied. Smaller standard deviation, small variance. So as that number on the bottom gets bigger, my standard deviation gets smaller. So I would get a tighter curve. Okay? Gives me a more accurate representation of where the middle is. All right, and how varied that information is going to be. Okay. So the bigger my sample is, the more accurate I have a better understanding of what my mean is actually going to be. Okay. All right. Let's do it. Actually, you know what? I'll do this one. I like this one better. All right, read the problem. All right, so let's look at A. What's the probability that a random selected bag of fertilizer will weigh between 14 and 16 pounds? How did I do it? I need to find my z-scores, right? Okay, this is actually chapter 8. This is what your test was just on. So we need to know what two pieces of information. So what's my mean? What's my standard deviation? Okay. And now to find my z-score, I need my x's, right? 14 and 16. So x equals 14. So my z is going to be x minus the mean divided by the standard deviation. Calculator. So 0.59. And then 16. This is negative 0.5. That's positive 0.5. All right. So next thing we have to do is we've got our z-score. So what do we do next? I go by chart, find my probabilities, right? Yeah, because it's 1 over 1.7. Oh, so it's the only thing that changed was it was negative in the first one and positive in the second one.
Oh, I didn't see the little.
Yeah, I because I put it afterwards. Hold on, let me actually make it a little better for the notes at the end. There we go. That's better. Because I didn't put the negative on my calculator because I knew it was negative and I didn't write it. All right, so we look up for negative 0.59. And we get 0.2776. Everybody find that on their sheet? Still need to find these. And this one should be 0.7224. All right. Everybody find those two? What do we do with them? Subtract them. So subtract those two because we're looking between. So 44.48%. So the probability that a randomly selected bag of fertilizer will be between 14 and 16 pounds is 44.48%. Okay. Does that process make sense? Because B is exactly the same thing. Instead of selecting one bag of fertilizer, I'm selecting a pallet. Okay. I'm going to look at 35 bags of fertilizer. So if I was to pick up an entire pallet of fertilizer, now I'm not looking at every single bag, I'm looking at the entire pallet. So I'd weigh the pallet, divide that by 35, and if it's between 14 and 16, right? But could one bag be less and one bag be heavier? Right. So when we're looking at a sample mean, that's what that means. We're not finding the actual weight of every single bag in it. We're finding the average of a group of things. Okay. So if I'm the one who's coming in and doing the actual study or the accepting the stuff into the warehouse, I'm not going to sit there and weigh every single bag because it would take too much time. I'm going to take a couple of pallets, weigh the couple of pallets, and make sure it falls into the right spot. If it is, I'll accept the whole ship. Okay? That's the point of doing a sample. Now, let's see how it actually impacts what we just did in the last one. So my standard deviation is still this, or my mean is still the same. And my standard deviation of the population is still the same. But since now I'm doing a sample of 35, I'm not just taking the standard deviation as is. I'm going to take that standard deviation and divide it by the square root of 35. Because that's that formula, the standard deviation divided by the square root of n. And you should get 0.287. If you don't, tell me. Our standard deviation is now smaller, right? So our graph should be more compressed. So between 14 and 16 should have a higher percentage of possibilities. After this step, it's all exactly the same as the last step. Yes.
Wait, you said that 0.287 what now?
That's the standard deviation of the sample means.
Okay.
So now we're going to do the exact same thing we did before, except we're going to use this new standard deviation. We're not going to use 1.70. So x is 14. So z is 14 minus 15 divided by 0.287.
That's all you do differently.
Yep.
And
That's actually, yes, that's all you're doing differently. It's actually what makes this stuff so difficult down the line. Is because if you notice, even when we did chapter 8, the proportions was basically the same to find your z-scores. The direct, or the ones where they were discrete values, it was basically the concept of finding the z's and the probabilities are all the same. It's just one little thing you have to do beforehand that's going to change it. So you have to figure out what process you're going to do it.
There's going to be multiple ones that are like one simple.
Right. It's like, it's this one. It's like, these are the exact same problem. The only difference is it says 35 bags instead of 1. Okay. And you have to, okay, now I'm looking at a sample, not just looking at individuals. So I have to divide it by the square root of the 35. The one nice thing I will say is, what happens if I divide it by the square root of 1? What's the square root of 1? 1. And if I divide something by 1, does it change? No. So you could just divide them all by the square root. And if you're only looking at one bag, just put n as 1. And it's not going to change anything. So it makes you do one extra step because you have to now divide by the square root of 1. But it doesn't, you then only have to remember one type of thing, which will help you, I think, sometimes in some situations. All right, I believe your sheets go up to 3.49. All right, so you should be able to find the probabilities for these two z-scores.
First one is 0.00.
Should be 0.9997. And then we're going to do what to these? So 9994. So if I weigh just one bag, there's a 44% chance that it's going to be between 14 and 16 pounds. But if I weigh pallets, there's a 99.4% chance that the average of those bags will be between 14 and 16 pounds. So which one is easier from a monetary standpoint? You weighing every bag or you weighing a pallet of bags? The pallet of bags, because I only have to weigh it once. Okay. And as long as it's 99.4 chance that it's going to fall between those. So if a truck comes off and I weigh two of the 20 pallets on there and they're good, I'm good. I'm accepting the whole thing. Okay. Because the chances are that it's going to be good. That's how most situations are done. They don't look at everything. And actually, I'm talking about pallets because it was 35 bags, but when you get shipping containers off, they'll weigh the whole shipping container. Or they'll weigh the whole truck. And it's like, because they know if it's all one type of thing on there, then they can determine does it work or not. Okay. So you can see how by changing that standard deviation or changing the sample size, you can actually get a lot more accurate representation of it, or a more precise calculation.
So in theory, that 35 could get it.
Yeah. Yep. All right, let's do another one of these. We did the fertilizer. Let's do. Oh, it's almost Thanksgiving. Let's do turkeys.
We have class that week.
No. Nope.
What do you mean now?
Week of Thanksgiving? We don't
Yeah,
have
we
class.
do.
Well, you don't have my class. Let's put it that way.
Because our class is Wednesday, but we have school Wednesday. I was looking at the schedule.
Okay. I'm telling you right now,
Yep.
we don't have my class. We won't have class on Monday or Wednesday that week. I give you the week off.
Before Thanksgiving, right?
Yes, not after, before. So for my class, you have the week of Thanksgiving off. I know a lot of people had to go away and stuff like that and travel and things like that, so it's just easier. So, all right. Turkeys found in a particular county have an average weight of 15.6 pounds with a standard deviation of 4 pounds. 45 turkeys are randomly selected for a county fair. Find the probability that the average weight of the turkeys will be less than 14.5 pounds, more than 17 pounds, or between 13 and 18 pounds. All right. Find me my answers. Try it. Try it.
I don't know how.
Find me my z-score.
Don't know how to do that, obviously, if we eat on the test.
Okay, I haven't even looked at your work yet. That doesn't mean you've so what's the formula for z-score? Look at your note card. Or you did not write down the z-score formula.
I did.
Okay, then use it. If you don't try, you're never going to fix mistakes you make. This is your opportunity to try and not worry about getting it wrong.
Bless you.
Your mistake is your calculator. I can tell by your work right here. That's the formula, correct formula. Your mistake is how you typed in the calculator. So do that z-score for me and get me 0.59. So I can fix you how to show you how to use your calculator to do it. That's your mistake. I can see it right here.
We'll go back to the other.
I will in a second. I want you to do this one on your calculator right now because I want you to be able to get that answer.
You can go back. I got it.
I didn't want to be that guy,
I
but
got it, I got it.
I have bad memory.
14.5. 14 minus 16. 14 minus 15
And then
over 5.
it was
Oh, it was over 1.7. Sorry. 16.
16.
So z equals
So. This is.
okay. That's not the formula we're using because we're not looking for x. We're looking for z.
Z.
So
Okay.
z equals x minus the mean.
X minus-
Yeah, that's the formula. X minus the mean.
I thought it was times mean.
No, this formula is finding x.
Oh,
We know x. We're finding z.
oh.
That's not the formula you need. It's x minus mean over standard deviation.
That would be 14, 15.
1.7. You didn't write that. That's right. Now, type in your calculator. Okay, stop. Because that's not the right answer. I'll tell you what your calculator's doing. Your calculator's doing your order of operations. What's the order of operations? Have mass. Multiplication, division, addition, subtraction. It's dividing 15 by 1.7 and then doing the subtraction. That's not what you want. Okay, so you have one of two ways to do this on your calculator. My suggestion is do it in pieces.
Okay, so hit.
So let's do
this
this
and
on
then
first,
equal
right? So 14 minus 15
equal.
equals divided by 1.7 equals, and that's the correct answer. That was your mistake. Back, which was the number that, well, it's 0.59, this
Okay.
2 places. Okay, so now I'll do the first one. I'm going to slide it up, but I'm going to actually write the other numbers down below in a second. So I would help if I actually wrote them first. Step one, find your standard deviation of the sample means. So 4 divided by the square root of 45. That's your standard deviation.
Should I know about it then?
Oh, you're right. It does come out to be 0.6. I missed the 6 at the end. It does come out to be 0.6 if you round correctly. I just looked at the 5.9 and go, okay. I totally didn't look at the 6 afterwards. So there you go. You're all right. So now we have to find our z's. That's not your z. That's to find the standard deviation. No, you can't. We can't do this yet because we're not dividing by 4. This is correct for z. That's we're not using the 4 as the standard deviation because we don't have. We're not just looking at one piece. We're looking at 45 turkeys. It's at the very end of the problem. 45 turkeys are randomly selected for the county fair.
Oh. Then we go question.
It also doesn't help that it's in words and
I
not in
know.
numbers. Yeah, just looking for the key pieces of information. All right, so my x is 14.5, so my z,
So where did you get that number? I'm
the
confused.
14.5?
Oh, the pound.
Yeah, you had that.
Okay. Oh, okay, all right.
You actually did your z totally correct. You just used the wrong standard deviation because you used what they gave you instead of the calculation. So you'd have been looking at 1 turkey, not 45 turkeys.
So how did, like, I don't know how you got the,
0.60.
yeah,
It's the standard deviation for 1 turkey, which is 4. That's what they gave you in the problem, divided by the square root of how many turkeys you're looking at in this problem.
I don't know how to do that.
Type 4 divided.
Yeah,
Square root is the button, right? You have to second and then the x squared button on the right side.
yeah, I got it.
Okay. And then 45.
45?
Yeah. And then equals.
You don't put parentheses?
Nope. It'll automatically put the parentheses at the end.
0, oh. Okay.
I might have done the calculation wrong, but I got 0.63.
I'm going to do it just in case.
Oh,
So,
I would say don't trust you, but then I get them wrong too. So
no, I trust you.
it's, yeah, 0.596.
yeah, that's there. And then this calculation comes out to be negative 1.83 is what I got. Well, that's the z-score, the probability that goes along with that. Yes, I know. It's like, okay, we're looking at these. No, that's the z-score. Now we got to get the probability for it. So we're gonna look up negative 1.83. Negative 1.83, so 0.33 or 0.336. Yes? Okay.
Is it? Yes, 0.33.
Yeah.
0.0336.
All right. So now we wanted less than 14.5 pounds, right? So is that the correct number? Yes, because the graph, we typically are looking at the left, which is this case, so that is less. So that's the probability of that.
Now we gotta do the same thing for 17.
Yes. Yep. But the nice thing is, I don't have to redo the standard deviation. We already have that. The only thing that changes in this case is my x.
See, between 13 and.
Well, you found B?
Yeah.
Okay. So you have to do twice. You do 13 and 18. 3.33 is 0.9901. Is that the number I want?
Yes.
Kind of.
Oh,
That number's correct. It's not the number I want. I want more than 17. So I have to subtract it from 1. So I have to do 1 minus that. So this goes to 0.099. Yeah. Because remember, once you get the answer, then you have to decide what they're looking for. In this case, they're looking on the right side, so I have to do the 1 minus it. All right, last one. Don't worry, I have the answers already saved on another slide.
yeah,
It's too high.
yeah, it's too high. You can't do the, like, we
All
can't do.
So hold on, I shouldn't have erased everything. But that gives you information. So 13, so 13 minus 15.6 over 0.6. What is it? Okay, and then x equals 18.
And that one is 4.
So that's 4. So that's basically 0, and that's basically 1. So then the answer is basically 1. Or if you want to be like and not put 1, just put a bunch of 9s. So remember, 3 standard deviations is pretty much everything, right? Once you get past 3 standard deviations, it's in the rare territory, like extremely rare territory. So we're now 4 standard deviations on both sides. That's extremely rare. So in essence, you're always going to, those 45-pound turkeys are always going to be between 13 and 18 pounds on average. Okay. So you can see how the connection, like it all goes back to that Z table and the Z score, those things. It's just a matter of how we find our mean, our standard deviations to be able to fit into that process. Okay, that's it. I will see you on Wednesday. Don't run away, Bridget.
Run.
Not yet. Don't run away yet. Gonna want to.
Have a good one.
You too.
Have a good present.
You too. You too.
Thank you.
You're welcome.
Where do you not want me to go?
I just don't want you to run away yet. I'll tell you in a second.
Have a good one.
You too. Come here. Now that you know how to fix your calc, now that you know how to actually do it in your calculator correctly, go home, do the test again. I opened it for you. Got one more shot.
At home, I will do tonight when I can.
You're welcome.
I really, really appreciate that.